Alright guys, welcome back to another lesson. Today we're going to be talking about heat and specific heat. So this ties into the chapter regarding thermodynamic properties. So we've talked about internal energy, we're going to at some point talk about Hess's law, but one of the important parts of thermodynamics is an understanding of heat and what heat actually is, and then we're also going to talk about specific heat in this lesson. Which is sometimes also referred to as heat capacity. So this shouldn't be too long, but let's get started on this lesson. The first thing that's very important that we should talk about is heat versus temperature, because a lot of times students will tend to mix up heat and temperature. And it's very important that you know the difference between the two of these. So heat is not the same thing as temperature. Heat is a flow of energy that is caused by a difference in temperature. So when we talk about heat, heat is actually a form of energy. It's thermal energy. So I'll say that one more time. Heat is the flow of energy caused by a difference in temperature. Now, what is temperature? If heat is energy, temperature is not the same thing as heat. Heat is a form of energy, and temperature is a system for measuring heat, or the lack thereof. So temperature is actually a measurement system that's used for measuring the flow of heat and the direction in which the heat is flowing, system to surroundings or surroundings to system. And it's important that you can differentiate between the two of those, because they're not the same thing. Now, temperature plays into heat. When we start calculating heat for given reactions, we need to know a change in temperature. It's a measurement that plays into heat, but it is not heat itself. So how do we calculate heat? Heat can be calculated by the following equation that we see below here. Q is the symbol we use to represent heat. So the Q can be calculated using M, S, and delta T, and we're going to discuss what each one of these are. So M is the mass of whatever object is releasing or absorbing heat. So you should note that because mass is playing into this equation, heat and anything that is based on heat is going to be an extrinsic property. And remember, extrinsic means it's not inherent to the substance itself. It's going to vary depending on how much substance there is. And we see that with Q. So when we measure heat, it's going to depend on how much substance there is. The more there is, the more the mass is going to go up. S, which sometimes we see as C sub S or C sub X, there's a whole bunch of abbreviations. It's called specific heat. Sometimes it's referred to as heat capacity or specific heat capacity. And specific heat is the amount of energy in joules that it would take to raise 1 gram of a given substance 1 degree Celsius. So specific heat is actually intrinsic to each substance. So for instance, if I have water, I can have a whole pot of water, or I can have just a couple milliliters of water. That doesn't change the amount of energy required to raise 1 gram of that water 1 degree Celsius. Now, to raise the entire pot versus to raise just a couple of grams that make up the milliliter, or a few milliliters, that's going to be a big difference in energy. And that's why the energy itself is extrinsic, the heat. But the specific heat capacity, which is based on 1 gram of any substance to raise it 1 degree Celsius, is intrinsic. And then delta T, the delta or Greek triangle symbol is used for change in. That's what it means. So delta T is going to be a change in temperature. And we define delta T, which I'll write down here, as TF, which is the final temperature, minus Ti, which is the initial temperature. So you could have your final temperature actually being lower than your initial temperature. If that's the case, then you're looking at a decline in temperature. And so the change in temperature is going to be negative if you have a decline in temperature, where your initial temperature is a higher value, your final temperature is a lower value. So delta T can be negative if we are going into the negative direction. And I want to just point out some units here. So Q, heat, would have the unit of joules. All right. Mass is going to have the unit of grams. The T, or the delta T, is going to have Celsius. Now you have to be careful because sometimes we use Kelvin in our equations, sometimes we use Celsius. When we calculate heat, we do Celsius. And then, let's see, that was delta T. And then specific heat is going to be in joules per gram Celsius. That's going to be the unit for the joules. I'm sorry, that's going to be the unit for the specific heat. Alright, so let's try some examples like we normally try to. You find a pure copper penny in the snow at -8 degrees Celsius. You pick it up in your hand and the penny is warmed to 37 degrees Celsius. Assuming the penny is 3.10 grams and the specific heat of copper is 0.385 joules per gram Celsius, find the heat absorbed. So what we're looking for here is going to be Q. We want to find what Q is equal to. And so I listed here all of the knowns that we have. We know, if we come back to this equation, that Q is equal to mass times specific heat times the change in temperature, which is T final minus T initial. So let's go ahead and find each of those values. So we'll set it up down here. Q is going to be equal to the mass, and you want to make sure your mass is in grams, which it is here, so 3.10. The specific heat is the next thing. They give that to us in the proper units, and it's 0.385 joules per gram Celsius. And then we need the delta T as our last part. So the T final here is going to be 30, so let's put this as delta T, is equal to 37, that's T final, minus a -8 degrees Celsius. So a minus and a minus, hopefully you realize that comes together as a plus. And what we end up with, if you add both of those together, you should get 45 degrees Celsius. And that's a positive 45. It's positive because we started out at -8 Celsius and we went up to 37 Celsius. So when we take that climb, we're requiring an input of heat to the copper penny, and that's why we see a positive delta T. So you can take a minute, you're going to multiply these three values together, and you'll find what Q is in joules. So go ahead and take a minute, put that in your calculator. So hopefully you should end up with 53.7. And if we're minding the significant figures, notice that we only have 2 for the -8 degrees Celsius up here. So we could rewrite this as 54, and the unit would be joules. Now the unit is joules because the grams right here on the mass cancel with the inverse grams, so specific heat. The inverse Celsius on the specific heat will cancel with the Celsius for the delta T's. That leaves joules. And so the answer here would be 54 joules is the amount of heat, and remember heat's a form of energy, so it's the amount of energy that would be required to raise that penny to 37 degrees Celsius. So that's how much energy it would have absorbed from your hand in the form of heat. So let's do one more. You don't always calculate heat, although that tends to be one of the most common ways you use the equation. You could certainly find other pieces of information provided you're given all of your other variables. So let's take a look at this one. A container of water absorbs 1,880 joules in order to go from 20 degrees Celsius to 50 degrees Celsius. The specific heat of water is 4.18 joules per gram Celsius. What is the mass of water? And I just want to point out here, when we talk about calorie in a class, and remember calories in chemistry are different than food calories, which is a kilocalorie. A calorie by definition is the amount of energy that it takes to raise 1 gram of water 1 degree Celsius. So a calorie by definition is the specific heat of water. It's the joules that are required to raise 1 gram by 1 degree Celsius. So when you see calorie and the number of joules a calorie equals, you always see it's 4.18. And that value stems directly from the specific heat of water, which is defined as a calorie. So anyway, if we were to revisit this equation, this time we're being given Q. So we have Q. Q is 1880 joules. That is equal to, now what is it asking for? The mass of the water. So that's going to be equal to M. We don't know what M is, so we'll put that up here and we'll find it in a minute. And the specific heat of water is 4.18 joules per gram Celsius. And now what's our delta T here? It says that it goes from 20 to 50 degrees Celsius. So delta T, again, is final minus initial. Final here is 50 minus the initial, which is 20. So when I subtract the two of those, I see 30, positive 30, and that is in Celsius. It's positive 30 degrees Celsius is my delta T, because it was an increase from 20 degrees Celsius to 50 degrees Celsius. So what I'm going to do, I want to solve the right side of the equation and then isolate M by itself. So what you should do, take 4.18 and times that by 30 in your calculator. And when you do that, you should get 125.4. Then you're going to take 1880 and you'll divide that by the value that you just got. And that'll give you M. So I'll take a minute, finish that up in your calculations. And you should see that M comes out to 15.00. So you might have 14.99, we round that up. It would be 15.0. And again, minding significant figures, the most we have here is 3, so we would report 3 here. It would be 15 grams of water is the amount of water that would be present. So I hope you guys found this instruction useful. This is how to calculate heat, the difference between heat and temperature, and a little bit on specific heat. So as always, thank you very much for watching. Please remember to like the video if it helped. You can leave comments if you found something useful, if you have any questions. And always, as always, the best way to get up-to-the-date information on when I post stuff is to subscribe to the channel. So thanks a lot, guys, and I'll see you in the next lesson.